Hey everyone, good morning. Welcome to lab. So I'm going to go ahead and share my screen here. Does anyone have any questions before we get started on the? So today we'll be looking at continuous by continuous interactions. So interactions when you have two continuous variables, as opposed to when you have one categorical and one continuous, which is what we looked at last time. Again, I'll be posting detailed handouts of how to do this stuff in SPSS and SAS, as well as the syntax that accompany those handouts. Just as with lab from last week on categorical variables and interactions between categorical and continuous variables, there's a lot, and you don't have to remember everything. The point is to give you all the tools that you'll need for the final project. And so if anything jumps out at you and you go, yep, that's the question that I'm interested in, it sounds something like that, then you'll know where to focus your attention more when you're doing the final project. But just remember to ease some of the stress that you don't have to remember all of this stuff. So I'll be posting those materials after lab, and then I'll be posting this recorded video later on today. All right, so are there any other questions before we get to the lab? All right, so I'll go ahead and share my screen here. Okay. And real quick, can you let me know if this PDF is popping up and going away?
Yes, it is.
Okay. Thanks, Marcus. All right. Okay, so again, this lab is going to be on continuous by continuous interactions. We're going to look at interactions between two continuous variables and how to run a simple slopes analysis to test differences at different levels of a variable. And that will make a lot more sense as we get into the lab. This example, again, was taken from Leona Aiken. It comes straight from her textbook with Steve West on testing and interpreting interactions, as well as the Cohen-Wesson-Aiken textbook. The data set that we'll be working with is called exmp8dat.txt, so example 8dat.txt. And the variables that we have in our data set, we have subject number, we have x, which is a continuous predictor, we have z, which is another continuous predictor, and then we have y, which is our continuous criterion. And so here's a look at what the data look like. So again, it's a text file, and as we've been doing, we'll be specifying the different widths here. So here, subject number would be 3 spaces wide, because if we start here and we click over to the right, it's 1, 2, 3 spaces. And then the next variable will be 1, 2, 3, 4, 5, 6, 7, 8. So that's how you count the different widths when you're reading in a fixed width format data set. All right, so first we'll load this package here, the psych package. We'll need that later. And then here I'm going to create an object. This is going to be my data set. So I'm going to call it my data. And I'm going to use the read.fwf function to read in my fixed width format data set. Again, I put all of my data sets in the C drive in the datasets folder. And then here I have example 8dat.txt. That is the file name for the data set. Just as I mentioned, we'll have to specify the widths. So the first variable, which is subject number, is 3 spaces wide. And then the rest of the variables, x, z, and y, are 8 spaces wide. I'm going to include some column names. So we have subject number, x, z, and y. There is no header because there's no line of variable names at the top of our text file. And then I do not want to skip blank lines. So this is false, or F for short, and then this is also false, or F for short. I'll go ahead and read this in. And real quick, we can see here, can you see this data set, the text file? So we can see here that everything read incorrectly. So we have 781, and then we have 8, and then here we have 2.6087, 9.2465. So this seems to match what we have read into R. So we're good there.
Hey, Patrick, quick question. Is this language you're using around read in, does that apply to the other systems like SPSS? Wouldn't we just open the data set? Or I guess I've been struggling with this the whole time.
Yeah, in SPSS, you could just open the data set and then you can find stuff to it. In SAS, you can do the same thing where you just open up the data set with point and click. But some people in SAS like to use syntax to read in the data set. So I think if you just open it with point and click, you can just continue to do that. This doesn't matter.
Okay, thanks.
All right. So we have my data read in. We have 150 observations. We have 4 variables. And then so what we'll do first is we'll fit our full regression model, which is X and Z, and the interaction between X and Z predicting Y. And the reason why we're doing that first is to see if there's an interaction term, if there's a significant interaction term, because if there is, then we'll do a little bit more probing to see what's going on with that interaction. So it's not the same, but it's sort of related to when you have an omnibus test, and then when you find something significant, you continue on with more tests to get a more in-depth view of what's going on with the data. All right, so here we'll print out some descriptives. We're going to be centering our variables. So if you're using other programs or if you want to do it by hand in R, you'll need the means to center the variables. Because remember, to center, all we're doing is subtracting the mean from each score. And what that does is it moves the mean of the variable to 0 so that our interpretations are a little bit more meaningful. All right, so I'm going to center X first. So I'm going to create a new variable in the my data dataset, and I'm going to call this variable xcent. And I'm going to use the scale function to scale X in my original dataset. And so I want to center it, but I don't want to scale it. So make sure that center is equal to true and scale is equal to false. We're going to do the same thing here for Z. And then to compute the centered interaction term, which I'm going to call xzcent, I'm going to multiply my newly created xcent variable by the newly created zcent variable. So we have x centered here, and then we have z centered here, and then we have the product of the 2 newly created centered variables. Now we can run descriptives again. And as you can see here, the means now of xcent and zcent are 0, which is what we want. And then the mean of the interaction term is 0.81, but that's not supposed to be 0. Another neat thing about centering your variables is that, as you can see here, to get the interaction term, we multiply the 2 variables together. And so sometimes that can lead to multi-collinearity issues because the predictors will be highly correlated with this interaction term here. So when you center the variables, it actually reduces the correlation between the interaction term and the individual predictors. So that's another neat thing about centering. All right. We can look at our correlations here. And like I said, if we look at the correlations between xzcent, so this bottom line here, and we look at the correlation between that and the individual xcent predictor, the correlation is almost 0. And same thing here with zcent, it's almost 0. Okay. And then just to describe what happened in this correlation function, so we ran the correlation function on the my data set. Use equals complete .obs is listwise deletion. So we want to delete anyone or any row that has a missing value. And then we want Pearson correlation. So method equals Pearson. All right. So what I'm going to do first is I'm going to fit the full regression model. I'm going to call it reg1. I'm going to use the lm function. And I'm going to predict y from xcent. the x-centered variable, the z-centered variable, and then the interaction term between x-centered and z-centered. The data set is my data. Go ahead and run that, and then I'll request a summary of reg 1. And then here we can see, oh, sorry, I just saw a question that came in the chat. Do we need to center the data every time before we run regression? You don't have to center the data. If you're looking at interactions, it will help a lot. So you can not do it, but it'll just make things harder for you. So I would suggest centering if you're going to be probing for interactions, whether the predictors are categorical or continuous. Okay, so we have our full regression model here. And remember that this coefficient here is the relationship of x-cent with y when we're at the mean of z-cent. Because remember that 0 is now the mean. So now we can say that at the mean of z-centered, this coefficient is the relationship between x-centered and y. And then here we have our interaction term. So what we want to look at here is, the first thing we want to look at is the interaction significant? And so here, our p-value is really, 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 really small. And so we can say that if there's a significant interaction between x and z, such that the values or the relationship between x and y is partly dependent on the value of z. And then so since this is significant here, we want to proceed with a simple slopes analysis to see how the relationship between x and y differ at different values of z. And I'll be plotting this later and it will make a lot more sense. I know right now it just sounds like a lot of words, but once we get into the plotting, it'll make a lot more sense. So remember, what we're going to focus on here is we're focused on the relationship between x and y at different values of z. So you can flip it if you want and look at the relationship between z and y for different values of x. But for this specific example, we're interested in x, the relationship between x-centered and y that is moderated by z. Okay, so the first thing that we're going to want to do is we're going to collect our first simple regression equation. And so this is the slope of our first regression, of our first simple regression equation, and then this is the intercept. And this simple regression equation is at the mean of z-cent, or it's at the mean of z, because we have centered our z variable. All right, can everyone see this PDF here? All right. So I'm going to have all of our simple, we're going to collect 3 simple regression equations. And so the first one is at the mean of z-cent, or it's at the mean of z, because z-cent, or z is centered at 0. So y hat is equal to 0.548 times x-cent. So that's our coefficient here, 0.548, plus our intercept, which is 6.389. And to test the significance of this simple regression equation, which is this slope right here, we can simply look at the t-test, which is 9.85, and the p-value is super, super small. So what we can say is, at the mean of z, the relationship between x and y is significant. Any questions about this first simple regression equation and the interpretation? Okay. So again, this is our first simple regression equation. We have pulled these coefficients from the model where we have x-centered, z-centered, and the interaction between x-centered and z-centered. And what this simple regression equation represents is the relationship between x and y at the mean of z. Okay. We have ANOVA functions here for the sum of squares if you need it, and confidence interval functions. And so for all of the examples, I'm going to skip over these because they don't really contribute to the example. but they're there in case you need it. And then here, this function bco gives you the variance and covariance matrix of the coefficients. I'll just show you this real quick, but you don't need to worry about this too much. So this is a covariance matrix of the different coefficients. So we have x-cent, z-cent, and x-z-cent. So remember, this isn't the covariance matrix of the data or the individual variables. It's how the coefficients are related to each other. Again, this doesn't really matter, but the reason why I show it here is because if you want to calculate standard errors by hand, you can use this matrix to calculate the standard errors, but we won't be doing that. We'll be tricking the software into giving us the standard errors and the appropriate t-tests, so we don't have to worry about all this mess here. Okay. So what I'm going to do is, now that we've seen that the interaction is significant, I'm going to use some plots to kind of get a better idea of what's going on here. So I'm going to plot x-cent against y. Here's a title, scatter plot x-cent with linear and low s. And then I'm going to use the AB line function to add a regression line. And the regression line is going to be a regression line that predicts y from x-cent. We're using my data, and then I want that line to be red. And then I'm also going to plot a low s line using the lines function, which is wrapped around the low s function. And I want to look at the relationship between x-cent and y. My smoothing parameter, which is f equals, is 2/3, and the color is blue. So for the smoothing parameter, you could just keep it at 2/3. You don't ever really have to change that. All right. So here's the scatter plot in the bottom right corner there. I'll zoom it after I plot the lines. There's our regression line and then our low s line. So it's nice to have both the regression line and the low s line, because the low s line will show if there are any patterns in the data. The regression line sometimes gets flattened out when there are two opposing relationships. So sometimes it'll hide some of the things that are going on in the data. So it's good to plot both just to get a better idea of what's going on. All right, so the main point here about this plot is that we have butterfly heteroskedasticity. So as x goes from low to high, actually, let's look at it this way. As x goes from the mean outward, whether it's toward positive values or negative values, the variation in y increases. And so it sort of looks like a butterfly, where it's wider out here at the ends than it is in the middle. And the reason why that's important is because that's indicative of a interaction. So we've already seen that the interaction term is significant, and this plot is just furthering that, that suggestion. I'm going to do the same thing here with z-cent. So I'm going to plot z against y, and then I'm going to plot my regression line, and then here my low s line. I'll just go ahead and run these lines all together. And then we can see again that we have a bit of butterfly heteroskedasticity, where as z goes toward negative values from the mean or toward positive values from the mean, the variation in y tends to get a little bit more spread out. So we have wider scatter here and out here, and then less in the middle. Any questions about those plots?
Well, I guess in terms of steps, you plotted the relationship between z and y as well. Is that what you just did in the second one?
What was that?
The second plot was between which variables?
Z and y.
Z and y. But you didn't, we didn't look at a regression equation for z and y, but would we in the same way that you did the x and y regression equation?
Right, that's a good question, yeah. So we are focusing on the relationship between x and y, but because the interaction term is x times z, it's good to look at the individual plots between x and y and z and y. So this step isn't really necessary for every single interaction, for every single time you're plotting an interaction, but I think Leona included it in here because she just really likes plots. So yeah, so you're right in that we're not really worried about the relationship between z and y, but because the interaction term does contain both x and z, just for completeness, it's nice to look at both the plots.
Thanks.
All right, so the next plot that we're going to look at is a plot of the residuals against the predicted scores. So I'm going to plot, I'm going to create this new data set called my data underscore resid. And as a base, I'm going to start with my data. And then I'm going to add a new variable called resid. And those will be my residuals, which I get by running the residuals function on my regression model, which is reg1. Similarly, I'm going to create this new variable called pred, which will be my predicted values. And I get those by using the predict function on my regression model here, reg1. So again, I'm creating a new data set just so that I don't overwrite my original data set. As a base, I'm going to use the original data set, and then I'm going to add resid and pred. And I'll show you what that looks like. So I'll run these 3 lines here. And then if we look at my data resid, it's the original data set, but now I have this resid variable and predicted variable. And so I'm going to go ahead and plot those. So I'm going to plot the the predicted values against the residual values. Here's a title. And then I'm just going to superimpose a regression line and then a LOS line. Okay, the reason why we want to look at this plot is, if it loads, okay. The reason why I want to look at this is we can see that our LOS line and regression line kind of converge to the same evidence that including an interaction term gets rid of the relationship between predicted and residual, which is what we want to see. Because if we see a pattern here, then we know that there's something that we're missing. So this is just serving as evidence that including the interaction term is what we're supposed to do and is a good representation of what's going on in our data set. Any questions about this?
How are you interpreting this data? Like what type of scatasticity are you?
So this scatter plot is a little bit different. What we want to see is no relationship between the predicted values and the residual values. And given that there is no relationship, then we can be confident that the model predicting y from x, z, and the interaction between the two is an appropriate model for the data, because there's no relationship here between the predicted values and the residual values. So if we were missing something, like if there was some kind of like non-linearity, or if there was if the interaction term wasn't helpful or useful to add to our model, or if we were missing a predictor, then we might see a pattern in this plot here. So all we're looking for is a flat regression line and a flat LOS line. Okay, so we're going to continue with our simple slope analysis. And so we've already gotten our simple regression equation looking at the relationship between x and y at the mean of z. The next steps that I'm going to be, so it was way easier to look at the relationship between x and y when the z variable, or the third variable, when it was categorical, because you could just look at if everyone, for everyone who's in group 0, right? Like, let's just say we're looking at Democrats versus Republicans. So for everyone who is a Democrat, what's their regression line? And then for everyone who's a Republican, what's their regression line? But when we're looking at continuous variables, it's a little bit harder because the groups aren't discrete. So what we're going to do is we're going to kind of artificially make z discrete, and we're going to look at the relationship between x and y at one standard deviation above the mean on z and one standard deviation below the mean on z. And so at the end, what we'll have is we'll have a simple regression equation, one standard deviation below the mean on z, a simple regression equation at the mean, which we already have, and then a simple regression equation, one standard deviation above the mean on z. And again, this will make a lot more sense once we look at the plots. I think that'll tie everything together nicely. So the first thing we're going to do is we're going to create a new data set called simple. And again, I'm just going to use my original data set as a base because I don't want to overwrite that data set. And then I'm going to create a new variable called z above. And this is kind of counterintuitive here. The handouts that I'll be posting go a little bit more in depth into why this is, but I still don't quite get it all the way. But to get z above, we're actually going to subtract a standard deviation. We're actually going to subtract the standard deviation of z. The reason that is because it'll shift the 0 value to one standard deviation above by subtracting. So it's a little bit backwards. So I just remember that it's backwards. So again, to get z above, we're going to take our z-centered variable and we're going to subtract the standard deviation of that z-centered variable. And then to get the interaction, which I'll call xz above, we're going to take the x-centered variable and then multiply by the z above variable. So again, this is just getting our interaction term when we multiply x-centered by our new z above. So I'll go ahead and create these new variables, and then we can get descriptives. And so now I have the descriptives for z above and xz above. And we can see that all right. Yep, never mind, nothing there. Okay, here's the correlation matrix if you need it, but I'm not gonna run that. And then we'll just go ahead and fit the simple we'll fit this regression equation, which will trick R into giving us the simple regression equation for one standard deviation above the mean of z. So for reg 2, we're going to use the LM function to predict y from x-centered and the new z above variable, and the new interaction term, one standard deviation above the mean of z. So xz above, which we just created up here. And remember that this data set is now called simple. And then from this summary, we can get our simple slope, the intercept, and then we get the appropriate standard error for the significance test, which we see here, again, is really, the p-value is really, really small. And so we can say that at one standard deviation above on z, the relationship between x and y is significant. So here's our simple regression equation for one standard deviation above the mean on z. Its y hat is equal to 1.003 times x-cent, and that's this coefficient here, plus the intercept, which is 6.410. And again, so for one standard deviation above the mean of z, the relationship between x and y is significant. Questions about this simple regression? So we have one more, and that's the simple regression equation, one standard deviation below the mean of z. And so in my simple data set, I'm going to create another variable called z below. And remember that it's backwards. So we're going to take our z-centered variable and we're going to add the standard deviation of z cent. That'll give us z below, which we'll use to get our simple regression equation for one standard deviation below the mean of z. I'm going to create a new interaction term for one standard deviation below the mean of z. And I will multiply x-centered by our new simple below, or simple, our new z below variable. And that will give me the interaction term needed to trick R into giving us that simple regression equation, one standard deviation below the mean of z. So I'll go ahead and run these lines here. We can get our descriptives. And now we have z above and xz above, which we did in the last step. And then here we have z below and xz below, our new variables. And so you can get a correlation matrix if you need it, but I'm going to go ahead and move on to getting simple regression equation here. So in this, I'm going to create a new object called reg3, and this will be a model predicting y from our x-centered variable, our new z below variable, and the new interaction xz below. Remember that the data set is the simple data set. I'll go ahead and run that and request a summary. And then here we get our simple regression slope, and then our intercept, and then we get our standard error. This is the correct standard error. And then our p-value, which this time is greater than 0.05, so it's not significant. So going back to this PDF here, one standard deviation below the mean, we have the coefficient of 0.094, which I drew from here. And then the intercept is 6.368, which is this intercept right here. And for this simple regression equation, what we can say is the relationship between x and y is not significant, one standard deviation below the mean of z. So essentially what we've done here is we've almost turned z into a discrete variable. So it's continuous, but we're looking at the relationship of x and y at the mean of this variable, one standard deviation above the mean of the variable, and one standard deviation below the mean of the variable. And as we'll see in this plot that I keep referring to that is in the near future, it changes. So at the mean, it's x and y are a little bit less related. They're more related at one standard deviation above, and it's the relationship becomes non-significant at one standard deviation below the mean. And so we'll see that in just a second. Okay. So what I'm going to do here is I'm going to create more new variables using our simple regression equations. So one thing I want to point out here is this new variable called ZL slope it's for Z low, and then I guess slope is what is the variable is called. But what this variable is if you look here at one standard deviation below the mean, which we'll call Z low, it's the coefficient, right, times the centered variable plus the intercept. So this right here is the simple regression equation for one standard deviation below the mean of Z. And so essentially what I want is I just want the predicted values at one standard deviation below the mean of Z so that I could plot them. And then similarly, we have this simple regression equation for the mean of Z at the mean of Z. We'll get the predicted values for those. And then I have the simple regression equation at one standard deviation above the mean of Z, which again, we want to compute the predicted values so that we can plot them and see what these relationships look like in a plot. So I'm going to create a new object called simple_pred. I'm going to use the simple data set as a base. And then I'll create ZL slope. So Z low, I'll create Z at the mean. and then Z high. And then here, I'm going to plot it, and I'm going to plot, I want to get the scatter plot for X against Y. Here's an X label, accent, and then a Y label, Y, and then a title. And then I want type equals N because I don't want to plot the points. I want the plot to be a little cleaner and just have the regression lines. All right. Just give it a second here. All right, so this is, again, this is our base plot. Hold on. Here we go. And the reason why, where is it? The reason why I use type equals in quotes N is so that there are no points on the scatter plot. I want it to be blank. And then I'll plot the regression line at Z, at the mean of Z. So to plot the regression line, I use the AB line function. Within that is the LM function, and I want to predict ZM slope from Xcent. And then our data set is simple underscore pred. And by default, I think the line will be black. And I'm going to do the same thing for Z low here, and I want that line to be red. I'm going to do the same thing here for Z high, and I want that line to be blue. And I'm going to add a legend here where we have ZL slope, ZM slope, and ZH slope, and the colors are red, black, and blue. So I'll plot these one by one. And so this is what we've been getting at the whole time. So at one standard deviation, so this is X-centered against Y. So we're focusing on the relationship between X and Y. And at one standard deviation below the mean of Z, which we call ZL, the line is pretty much flat. So that's why our simple regression coefficient was non-significant. And at the mean of Z, ZM slope, we can see that the relationship is a little bit less flat. And then the relationship is strongest here at one standard deviation above the mean of Z. So essentially what we're saying is between X and Y, as Z increases, the relationship between X and Y gets stronger. And so that's why we went through all this trouble, is to see that. Are there any questions about this plot here?
Will you say the interpretation again?
Sure, yeah. So as values of Z increase, the relationship between X and Y also increases, so it becomes stronger. Because here, at one standard deviation below the mean of Z, the relationship is almost zero because the line is flat. And our simple regression coefficient was non-significant. And then as Z increases from one standard deviation below to the mean, the relationship gets a little bit stronger. So the line is a little bit less flat. And this regression coefficient, or simple regression coefficient, was significant. And then finally, when we go one standard deviation above the mean to Z high, the relationship is the strongest because it's the steepest line. The coefficient was also the largest. I think it was, let's see here. So one standard deviation above was 1.003, which is greater than 0.548, which was at the mean. So what we can say is the relationship between X and Y gets stronger as Z increases.
Thanks.
Any other questions about this plot or the interpretation? This is essentially putting everything that we just did together. This here is, it's the same plot, but if you want to have the points on the plot. So I'll just plot it real quick so you can see it. So same thing, it's just if you want the actual scatter plot on there. But as you can see, it makes the plot a little bit messier. And then this is the last thing that we'll go over. If you want to get the standardized coefficients for the regression. So this is kind of an aside, and I wouldn't really worry about this part too much. But if in the event your advisor or you're working on a project and you need standardized coefficients, this is pretty similar to what we covered earlier in the class, but it's shown here for completeness. So if we want to get the standardized solution, I'm going to create a new data set called standard, and I'll use my original data set as the base data set. I'm going to create a variable called z of x, and I'm going to use the scale function to standardize my x variable. So again, this is not the center variable, this is just the original x variable. So I'm going to standardize the original x variable, call it z of x. I'm going to standardize the original z variable, call it z of z. And then I'm going to multiply those two standardized variables, z of x and z of z, to get the interaction, which is confusingly named z of x, z of z. And then I'm going to also standardize the original y variable to get z of y. So go ahead and run this in one step. You can get descriptives if you want, correlation matrix if you want. And then here we'll run the regression equation so we can get the standardized coefficients. So reg 4, I'm going to run a model predicting z of y from z of x, z of z, and z of x times z of z, which is the interaction. And then my data set is called standard. I'll request a summary. And then these are my standardized coefficients. So if you were to go through the whole process again of what we just did, you can get the standardized coefficients by doing this instead of, or layering this approach on top of all the work that we just did. But again, you don't have to standardize unless, it's not really necessary to standardize. And I personally like to use the raw coefficients. But if in the event you ever need to standardize your coefficients, this is how you would do it. And so we get the standardized coefficient for for x predicting y, controlling for z, that's 0.558. The standardized coefficient for z predicting y, controlling for x, that's 0.008. And then the standardized coefficient for the interaction term, which is 0.46. All right. So that's the lab. Are there any questions?
In next time, or at one, I'm assuming we'll have a next time, will you go over how to write this up, or
for the I wasn't planning on that, but yeah, but I could do that. I think I'm going to go through the handouts again that I'm going to post after this. There's a handout that goes through this in SPSS, and there's a handout that goes through this in SAS. And I believe that the interpretations are in there. So I'll double check that. And if the interpretations aren't in those documents, then I'll create a document with all of the interpretations that we just talked about.
Okay. And we graph it just to see it, so we understand what, but we probably don't need to graph it, right? In terms of interpreting, if we can look at the regression equations and significance.
I think practically, I think it's a good tool for reviewers. Like if you're submitting a paper, it makes the point really clear. And I think imagine we ran all of those different regression equations and extracted all of those different simple regression equations. And so it all looked like this at the end. And you can show all of this just through the plot. So it's a really powerful plot. But you're right, yeah, you don't have to plot it. I just think it's a really useful tool when it comes to submitting a paper for publication.
So you would typically submit the whole process you went through. You might even include that graph in your paper?
Mm-hmm.
Oh, okay.
Yeah, if there's an interaction, so if the focus of your paper is an interaction, yeah, then I would focus the writing in the body of the manuscript on the simple slopes analysis, especially if there's something interesting that's going on. And what I mean by that is, if the relationship between X and Y, for example, is changing based on the different values of Z, then the simple slopes analysis is useful. If instead what we saw were that, so if I go back to this plot here, this is a really good question. So if instead I saw that the black line, the blue line, and the red line were all the same, like they were just overlapping, then this is not useful at all.
There's no interaction, is what you can say.
Yeah, exactly. So it's sort of like that omnibus approach, where if you find a significant interaction, then you could go through the simple slope analysis to see if there's something interesting going on. But you're right, if there's no interaction, then there's no need to go through this process.
Thanks.
Mm-hmm.
Do you always test for interactions, or like how we looked at the beginning, because the data was kind of spread on both sides, then that would give you cause to investigate if there's an interaction effect?
So that's a good question. I would say that the number one reason you would include an interaction term is because theory says that there should be an interaction, or you have a hypothesis where there should be an interaction. Because imagine this is only 2 predictors, and so when you start to increase the number of predictors, the number of interaction terms, like you'll have 2-way, 3-way, 4-way interactions, depending on how many predictors you have in the model. The number of interaction terms that you can look at will grow exponentially. And there's no way that you can probe all of those interactions. And I think this was a point that you brought up in class, Marcus, but there's interactions are you're bound to find some that are just by chance significant. And so I would focus my attention on the interactions that either theory says should be existing in our population of interest, or if you have a hypothesis where you believe there to be an interaction, then I would include that. All right, any other questions before we wrap up here? Again, I'll be posting all of the handouts for SAS and SPSS online, along with syntax for those programs. I'll be posting this syntax online as well, and I'll be posting this video later on today.
Did you show, is this what you just showed us? Is this probing, or have we not gotten to that yet?
Yeah, that's a good question. Probing, I don't know. To me, probing just means like taking a deeper dive into the interaction, into the significant interaction if you have one. So I would say that what we did last week too, for categorical by continuous interactions, that is also probing, because you're looking at the relationship of X and Y based on group membership. So I would say both are probing. It's almost like if you find a significant interaction, you're looking deeper into it to see what might be going on.
And by looking deeper into it, can you going through these steps of looking at these new regression lines and looking at the graph?
Right, yeah. Exactly. So for continuous by continuous, probing would be a simple slopes analysis, which is what we went through here, where we estimated the different regression equations and extracted our simple regression equations. For categorical by continuous, it would be looking at so if you have a binary grouping variable where it's, for example, Democrats and Republicans, probing would be looking at the regression for Republicans only, and looking at the regression for Democrats only, and seeing if there's a difference in the intercepts or the slopes.
Thank you.
Mm-hmm. All right, well, if there's nothing else, then that concludes lab. I'll be sticking around for a little bit to answer any questions if anyone wants to. Thanks, everyone.